catch 'em all.
Also, we know that when the electromagnetic wave gets into our black body, that cavity wall, it makes many reflections to absorb all its energy. Then the body gets this energy and its temperature rise, and then our body, respect to its temperature, radiates. We call this is black body radiation. But this black body radiation have a problem, and this problem that we call ultraviolet catastrophe. What is ultraviolet catastrophe as a definition? Is the failed prediction of classical physics that energy radiated by a black body at extremely short wavelengths, means when wavelength gets shorter, is extremely large, and that the total energy radiated is infinite. Means while the wavelength gets shorter, energy radiation is infinite. But this problem is studied by Max Planck. Max Planck later developed a formula for black body radiation that was in complete agreement with experimental data at all wavelengths, by assuming that energy comes in discrete units or is quantized. Also, the Max Planck's develop about this problem later also will be accepted by Einstein. Also, we're gonna use this model later on about the atoms. Here, sorry, you see two graphs, and this graph shows that at the right hand side, blue line. This blue line is the classical theory. Means the classical physics and their formulas, they says that while wavelength gets shorter, as you see, the energy, means intensity of light, increases, and extremely low wavelengths, as you see, the line rise and rise, means becomes infinite. But as you see at the right hand side, there are some red spots. These red spots shows that these are experimental data. Here, means experiments show that the value of intensity of light and the wavelength does not increase always. After a value, it started to be decreased, and this is out of our classical theory. And the scientists call this as an ultraviolet catastrophe. Why? At the left hand side, you see that there are three different lines, and they represent different temperature and their intensity and the wavelength diagram. As you see, at the 2000 Kelvin, the line goes to peak value about or between 1 and 2 micrometer of wavelength. But at the 3000 Kelvin, the peak value approaches through the left hand side, means wavelength gets shorter, and 4000 Kelvin the graph rise and the peak value approach to visible light spectrum. Means at the 4000 Kelvin we can see that the object emits red light, and then it approaches to yellow, but later on wavelength decreases. But there is a problem, as you see. Normally classical physics says that, by this line that now I will draw, normally classical physics says that this line needs to go through infinite intensity and energy, but the experimental data shows that intensity decreases while the wavelength decreases. And this problem starts at the region of violet color spectrometer. That's why, at the violet color, that's why they called ultraviolet catastrophe. Now, after this point, we're gonna watch a video about blackbody radiation and ultraviolet catastrophe.
Extremely hot objects, such as these coals, emit visible light. It may surprise you to learn that all objects at any temperature above absolute zero also emit radiation. The coals are at a temperature of roughly 4,000 kelvins. The intensity peak of radiation for this temperature is in the range of yellow and red wavelengths. This means that an object at this temperature will glow orange. At lower temperatures, the peak is in the infrared, but enough red light is emitted for the object to have a dull glow. You can see this if you turn an electric stove burner up to high. Cooler objects give off little or no visible light, but are still emitting substantial amounts of infrared radiation. A jet engine might reach a temperature of 2,000 kelvins. Room temperature is just 300 kelvins. A very small amount of radiation will be emitted by objects at room temperature, and the peak wavelength will be in the very far infrared. Even though you cannot see it, your body is giving off radiation just like glowing coals do. It took a major theoretical breakthrough in physics to produce the curve you see here. Theories from 19th century physics, often referred to as the classical era of physics, were unable to predict correctly the amount of ultraviolet light observed in experiments. Max Planck resolved the problem, called the ultraviolet catastrophe, in 1900 by assuming that light energy was quantized. This was the first step towards quantum mechanics.